We start with a C function called prefix, which takes as input the pattern called P, its length called M, and the memory location called F, starting with which we store the array containing the failure function. We store the length of the current longest proper border in a variable called k, which we initialize by the special value -1. We fill in the cells from left to right. Recall that the length of the current longest proper border is stored in the variable k. At this point, we save it in the current cell of the array. Assume we have just filled in a position further on in the failure function. The variable k stores the length of the current longest proper border. We will have k loop through potentially all of the current proper borders, up to and including the empty border. We loop for as long as the current border cannot be extended by one symbol. To go to the next longest proper border, we find its length at position k in the array. There are now two cases to consider. In the first case, we have exited the loop due to the first condition becoming false, because none of the current borders, not even the empty one, could be extended. In this case, k has become f of 0, which is -1. The longest proper border at the next position is therefore the empty string, and we store 0 in the variable k. In the other case, the variable k stores the length of the longest proper border that can be extended by one symbol. We increment k in order to account for the extra symbol. The value of the variable k, which now holds the length of the longest proper border at the next position, will be saved into the array at the next iteration by the first assignment in the body of the for loop. Once all iterations of the loop are done, as the failure function uses one more position than the pattern, we fill in this last cell as well. We are now done with the code, but let us take a closer look at the conditional statement. In the positive branch, which is taken when k is -1, the assignment k becomes 0 is semantically equivalent to an increment of k. As the else branch also increments k, the entire conditional could be simplified and replaced by a single increment of k. By the way, this is one reason why -1 is a good choice for our special value at position 0. In any case, I find it easier to understand and explain the code using the conditional statement as is. But also keep in mind that the conditional is effectively an increment of k, and we will use this fact when we discuss the time complexity. Even if the code is seemingly quadratic due to the nested loops, a closer analysis reveals that it works in time linear in the size of the pattern. The key to understanding why lies in the body of the while loop. Consider an example pattern, some fixed index k into the pattern, and the value f of k. Because f of k is the length of a proper border of the first k symbols in the pattern, it means that f of k is strictly less than k. This means that in each iteration of the while loop, k decreases strictly, which we denote by a down arrow. Let us now concentrate on the body of the for loop. The variable k initially stores the length of the current longest proper border. It then potentially decreases due to some iterations of the while loop. In the conditional statement, the value of the variable k increases by 1 unit, as explained earlier, which we denote by an arrow pointing northeast called an up arrow. Therefore, each strict decrease in the while loop must correspond to at least one increase in the for loop, which means that the number of iterations of the while loop throughout the entire execution of the algorithm cannot be bigger than m, the number of iterations of the for loop. This can be better understood by using a visual argument where we track the decrements and increments of k. Each of the two operations takes constant time, and these two operations together dominate the running time of the algorithm. Therefore, it is sufficient to count the number of arrows to obtain the running time. I will draw the two types of arrows against a plot of the failure function for an interesting pattern. The x-axis represents the length of the prefix of interest, and the y-axis represents its longest proper border. The y-axis starts at -1 instead of the usual 0 because of the special value at position 0 in the failure function. Let us start with the iteration where I is 0. We store -1 in the array. We do not enter the while loop at all, and we increment k. We represent this increment by an up arrow in the plot. Go to the next iteration where I is 1. The value of k is initially 0, and we store it in the array. It represents the empty border of the current prefix. The while loop tests whether the current border can be extended by one symbol. Because it cannot be extended, k drops to -1. We represent this operation in the plot by a down arrow. Finally, k is increased by 1 unit, which we represent visually in the plot by an up arrow. In the following 3 iterations of the for loop, the longest proper border is extended by 1 unit, without ever entering the body of the while loop. Therefore, we add 3 up arrows to our plot to account for this behavior. Things get more interesting when we reach position I equals 5. At this point, the current border, which is ABA, cannot be extended. So we enter the while loop. In the while loop, we decrease k to go to the next longest border, which is A. We account for this decrease of k by 2 units using a longer down arrow. The current border, which is now A, cannot be extended either. So we decrease k to go to the next longest border, which is the empty string. We account for decreasing the current border by adding a down arrow. The current border is empty, and it cannot be extended either, so we decrease k and add one more down arrow, reaching -1 along the y-axis. At this point, the while loop exits. The value of k is set to 0, which is effectively an increment by 1 unit. We represent this graphically by an up arrow. In our example, it so happens that the decrease from k equals 3 to k equals 1 takes place in a single step, but it could have easily taken more steps, so let us take the pessimistic view that the decreases in k take place as slowly as possible. We replace the fast decrease in k by several smaller decreases. Because of this approximation, the number of arrows is now an upper bound on the exact running time. The next 3 iterations of the for loop see the border increase by 1 unit in each step, without ever entering the while loop. So we add 3 more up arrows. At the next position, the border is ABA. It cannot be extended, so we decrease k to go to the next longest proper border, which is A. We add a down arrow to account for the decrease in k. The border cannot be extended, so we add one more down arrow. The current border is now the empty string, and it can be extended. We increment k and add an up arrow to account for the extension of the border. There was no need to go all the way down to -1 this time. As before, we will take the pessimistic view and replace the longer down arrows by several unit down arrows. At the final position, the current border can be extended directly, and we add one arrow to account for this. Let us now analyze the plot in more depth. Each up arrow represents one increment, and there is exactly one increment for each position in the pattern. Each vertical sequence of down arrows represents a run of the while loop. At any given point, the number of down arrows is limited by the number of previous increments. But the increments are very slow. There is only one increment for each position I in the pattern. Each down arrow must correspond to some up arrow. Some up arrows potentially remain unmatched. So there are at most as many down arrows as there are up arrows. But there are exactly m up arrows, and therefore at most 2 times m arrows overall. As each arrow represents one unit of time, it follows that the running time of the preprocessing phase is big O of m, which is linear in the size of the pattern. In the next installment, I will discuss the implementation of the core KMP algorithm, and also show that it has a linear running time by using a visual argument. Make sure you subscribe to the Truly Understanding Algorithms YouTube channel. If you have subscribed already, hit the bell icon so that you get notified when the next upload goes live.